Okay, welcome to our conference on carbon pricing, our two-day virtual conference sponsored by the Pardee Center for the Study of the Longer Range Future. My name is Jim Stodder. I teach law and economics related courses at BU's Metropolitan College, and I'm also a research faculty here at the Pardee Center sponsoring this conference. Geoffrey is our first keynote speaker. He is professor of social enterprise at Columbia University Business School, and he is one of the leading environmental economists in the world. Geoffrey has been writing on energy and the environment for over 40 years, which is about how long I've been reading him. He has both received awards from and been in the leadership of numerous environmental and international policy organizations, too many to list here. His webpage is on the program. The last two months have certainly shown us both the terrifying pace of climate change and what can be seen as minimal changes most governments seem prepared to actually take. Given this urgency, it might seem odd to ask our keynote speaker, what can economic theory tell us about our choices? But as I think our keynote speaker may show us, the deeper we get into the economics of climate change, into what value we put on the livelihoods of future generations, on what measures we are willing or unwilling to take to minimize the uncertainties we face and those that they face, then the more we leave the merely economic to ask questions about fundamental human values. So when it comes to economic decisions about the future of the planet, one can be forgiven for seeing God in the details, if one is inclined to look for her. But that means that there's a lot of devil in those details as well. So I feel honored to introduce today's keynote speaker, Professor Geoffrey Heal. Take it away, Jeff.
Thanks very much indeed, Jim. Thank you for the invitation, and thank you for that excessively kind introduction. Let me begin by sharing my screen. So, as you all obviously know, we're at the beginning a major energy transition, probably the biggest energy transition in human history. We're hoping that within the next couple of decades, we can transit away from the fossil fuels, which have been the source of energy to human society for the last 250 years, maybe even more than that, and move to a clean fossil fuel-free future. What my talk is going to do is make a series of observations about the economics of this. It's not a totally coherent talk. The observations don't all totally fit together, but they give you different perspectives, I think, on some aspects of this transition. So this is an outline of the talk. I'm going to give you some background information. I'm going to talk about decarbonizing the power supply in the US. I'm going to talk about carbon taxes and the pluses and minuses of carbon taxes and alternatives to a carbon tax. I'll end up talking about electricity pricing. The point I want to emphasize is that decarbonization means electrification. You know, electrification and decarbonization are effectively different sides of the same coin. If we want to move people away from using fossil fuels, we're going to have to move them to using electricity. And that means we have to think very carefully about the pricing of electricity. If we were to continue to charge for electricity the way we are at the moment, I think it would make the use of electricity in a variety of applications very unattractive. So we have to rethink our electricity pricing model, I'm going to argue. Okay, so a bit of background first of all. What I'm going to say is essentially 3 or 4 points. One is that decarbonizing the power supply is a great deal less costly than is generally thought. That we can, sitting here in the US, we can decarbonize the power supply at relatively little, if no additional cost. I'm going to argue that carbon taxes, on the other hand, are probably somewhat overrated because they need to be very, very high indeed, as much as perhaps $400 per ton of CO2 to be effective. And I'll try to explain why that is. So we need to look for alternatives to carbon taxes. And as I just said, I'm going to argue that decarbonization means electrification, so we have to rethink the pricing of electricity if we want really a widespread electrification. So what do we have to do if we're going to solve the climate problem? Well, we have to decarbonize power generation, we have to decarbonize transportation, we have to decarbonize heating. And by heating, I mean heating of space in buildings, heating of water in buildings, and heating of industrial processes. Here in the US, transport is now the largest source of CO2 emissions. So that makes decarbonizing transportation particularly important. Worldwide, it's the second largest source of CO2 emissions, but it's the fastest growing. So that makes it also doubly important to decarbonize transportation. Here in New York City, where I am, buildings are actually the largest source of CO2. It's the heating of buildings and the heating of water in the buildings that is the largest single source of CO2 in a big city like New York. And I haven't seen exact precise data for other cities, but my guess is that's true of most major cities. Deforestation and agriculture are also quite significant sources of CO2, but I'm not going to talk about those because they raise somewhat different issues from the sort of decarbonization issues. This just shows you a summary from what I just said, that transportation is, sorry, let me go back. Transportation is 28% of our CO2 emissions, electric power 27%, and the rest comes from commercial, residential, and industry in the form of heating processes, heating, for example, making steel, making aluminum, heating space, and heating water. So what have we done so far? How far have we come in this process of decarbonization? The answer is we haven't done very much so far. We're making some progress with decarbonizing power generation because, as I'll show you in a second, wind and solar power are now cheaper than coal and gas, and that's important step, landmark. Electric vehicles are becoming a reality in ground transportation, but they're still an appallingly small fraction of the market share, though a rapidly growing one. We've made effectively no progress at all with decarbonizing heating, space heating, water heating, whatever. Though interestingly enough, here in New York City, we have a thing called Local Law 97, which does actually require massive reductions in the emission of CO2 by buildings. The law was introduced 2 years ago. It'll be implemented fully by 2025. And the idea is that by 2030, there should be a huge reduction in the greenhouse gas emissions from major buildings in New York City. And there will be fines of up to $286 per ton of CO2 emitted for buildings that are not in compliance with Local Law 97. So although nothing has been done very much so far, there's something on the books which is beginning to kick in. And if it's implemented fully, could be quite effective by the end of this decade. I mentioned second bullet point here, no, third bullet point, sorry, that wind and solar power are now cheaper than coal and gas. And here's some data on this. This is actually quite an interesting diagram. It comes from Lazard's, the investment bank, from their website. On the vertical axis here, you've got the cost of producing a megawatt hour of electric power, going from $20 to $380 a megawatt hour. Horizontally, you've got years from 2009 to 2020. And each of these lines represents the cost in each year of producing a megawatt hour from a particular technology. The dramatic one here is this one, the sort of yellowish beige line, which starts at $359 a megawatt hour in 2009, is down to $248 the following year, $159 in 2011, and last year was all the way down to $37. And that, of course, is solar photovoltaic. The cost of a megawatt hour from solar photovoltaic sources has dropped from $359 to $37 in the last decade, making it the least expensive way of generating electricity in the United States today. Another one which is very interesting is this sort of purple blue line here, which starts at $135 a megawatt hour in 2009, is down to 83 by 2011, and is down to 40 last year. And that, of course, is wind turbines. So what you can see from this, looking at last year's data, the two least expensive ways of generating electricity in the US last year were wind at $37 a megawatt hour, solar at $37 a megawatt hour, and wind at $40 a megawatt hour. This green line here, $59 a megawatt hour, is a gas combined cycle power station. This brown line is coal at $112. And this line here is nuclear, $141. And this is gas single cycle, which is the conventional gas turbine, at $175. So wind and solar are 50% cheaper than gas, a fraction of the price of coal, a fraction of the price of nuclear, and a small fraction of the price of single cycle gas turbines. And that's all changed quite dramatically because of the amazing drop in the cost of solar power and an almost similar drop in the price of wind power. Incidentally, these numbers here are selected historical mean unsubsidized values. So these do not take account of any of the production tax credits and so on available for wind and solar. And their averages over the whole of the US. The cost of wind and solar varies quite a lot from location to location because the wind blows more strongly in some places than others. These are averages over all sites in the US. Okay, so given that bit of background information, what I'm going to talk about next is the cost of decarbonizing the US's electricity supply. Biden has said he wants the entire electricity supply to be carbon-free by 2035. That's 14 years from now. That's a fairly ambitious target. I want to work out what the cost is of doing something like that. What's the cost of replacing all of our fossil fuel plants by renewable plants? I'm going to argue actually that the cost is very, very low indeed, which is quite encouraging. So here's the basic data we're going to have to use for working this out. US has 1 terawatt of generating capacity. That's 1 times 10 to the 12th watts. And it produces about 4 billion megawatt hours annually. And as I said, this is transport of the biggest sources of greenhouse gases. Here's a table giving you the breakdown of power output, electricity output by power sources. So gas is the biggest single source, 33%, 28% comes from coal. We've got a variety of other things down here, but these are the 2 key fossil fuels here. Between them, they make up 61% of output. And I'm going to look into the cost of replacing that 61% by renewable energy. So I'm going to build enough renewable energy to replace that 61% of the power that currently comes from gas and from coal. And we're going to have to make some modifications to the grid. We're going to have to invest in energy storage and a few other things like that in order to make this feasible. And I'm going to assume that this replacement of fossil fuels is 50-50 wind and solar. That was initially when I made it an arbitrary assumption, but it actually turns out to be roughly the right way to do this. Now, in calculating the cost of doing this, I've taken some cost parameters. I need the cost of wind capacity, $1,600 a kilowatt hour, the wind capacity factor, which is the fraction of maximum output that a wind turbine produces on average, the cost of solar PV capacity and so on. All these numbers here I'm taking from the US government's Energy Information Agency and from their website. So these are all fairly sort of non-controversial, fairly straightforward numbers, probably all on the high side because most of these numbers, as I just showed you a couple of minutes ago, are falling over time. And these are last year's numbers. So the numbers for the next couple of decades are probably going to be below these. This, I think, is high. The Energy Information Agency gives the cost of solar capacity as $1.1 per watt. Incidentally, I've been teaching for the last 7 or 8 years, I've been teaching a course on the economics of renewable energy. The first year I taught that course, that number was $8. So just a few years back, it was $8 a watt. Now the Energy Information Agency is giving it as $1.1 a watt. When I talk to people in the solar industry, and I've got a lot of alumni in the solar industry, they say that's actually on the high side, that they're paying 80 to 90 cents for a watt of capacity right now. So I just bear in mind that maybe a slight overestimate. This is not from the Energy Information Agency, the cost of storage, the cost of battery storage. And I'll talk more about that a little bit later on. Okay, now we need to build enough capacity to replace this 61% of output that comes from fossil fuels. And in order to do that, we're going to have to build out the grid. Wind and solar power are rather regional phenomena. You know, the wind is strongest, for example, in the Midwest. The sun obviously is strongest in the South. And it makes economic sense to produce wind where the wind is strong and to produce solar power where the sun is strong too. If you do that, then you need to build out the grid a lot because you need to move electricity from the source to the source of demand. So we have to build out the grid. I'm assuming in my calculations that we currently have 200,000 miles of high tension lines in round numbers here in the US. I'm assuming we're going to increase that by 25%. So we build another 50,000 miles of high tension lines. That's roughly $2 million a mile. So that's $100 billion. So we're going to invest $100 billion in building out the grid. Those of you who sort of read the papers carefully might have noticed that the infrastructure bill, which is before the Senate at the moment, contains a provision for building out the grid equal to $73 billion. So they're playing in roughly the right ballpark, perhaps a little bit on the low side. So one issue, obviously, in moving to renewables, you have to build out the grid in order to cope with the fact that renewables are not best produced close to sources of demand. Second issue you have to deal with, obviously, is intermittency. Just to give a sense of how important this is, I've shown you here the total output of all wind turbines in the United Kingdom over a 4-month period. And the key thing about this diagram, obviously, is just the amount of the fluctuations. You know, you've got, they're producing almost 2 gigawatts here. A few days later, they're producing 1/4 of a gigawatt. And then they're almost down to 0. Then they're back up to 1.5 gigawatts, and down again, and up again, and down again. So obviously, integrating a highly variable source, energy source like that into the grid, where you have to match demand to supply on essentially a minute-by-minute basis, that's quite a challenge. There's a couple of ways of doing this. One, obviously, is to use energy storage. So, for example, the natural thing, just looking at this diagram, would be saying, okay, whenever we've got a huge peak in output, we will take that, and rather than putting it into the grid, we'll put it into some batteries and store it. And then whenever there's a trough in the output, we'll supplement the actual output by drawing on what we've stored in the batteries. The cost of energy storage has come down a great deal in the last decade. It's actually come down proportionally even more than solar power has, which is really saying something. This is data from Bloomberg. In 2010, you were paying $1,100 for a kilowatt hour of battery capacity. 2018, you were paying $176 for a kilowatt hour of battery capacity. Today, it's about $100 for a kilowatt hour of battery capacity. That's Elon Musk claims that Tesla is paying around about $100 for a kilowatt hour of battery capacity. So that's come down by a factor of 11, even more dramatic than the factor of 10 by which solar power has come down. It's still quite expensive, as you'll see. This is still quite a large, $100 for a kilowatt hour still makes large-scale storage quite expensive, but it's infinitely cheap relative to what it was a decade ago. So there's two ways, actually, of dealing with intermittency. One, as I said, is to store power from times of abundance to times of shortage. The other is to what we call spatial diversification. To give you a sense of what that means, imagine that we've got two locations where there are wind turbines, so location A, let's say, and location B. And we've got a strong negative covariance between the wind speed in these two locations. So when the wind is blowing strongly at A, it's not blowing at B. And when the wind is not blowing at A, it is blowing at B. So between the two of them, there's always wind, but sometimes it's at A and sometimes it's at B. So if you connect the two of them together and connect them to sources of demand, then you'll always have supply. So that's an example of what we call spatial diversification. Now, of course, you never actually get perfect negative covariances between different wind sources, but you can have negative covariances between different wind sources. And the pooling of the output of sources whose covariance is negative can be very important in smoothing the aggregate output. This requires some overbuilding. That's an engineering phrase, overbuilding there. What that means is if you take my simple example, if you've got, again, two locations, A and B, which have a perfect negative covariance, covariance of -1, then when the wind is blowing at A, you can supply entire demand from A. When the wind is blowing at B, you can supply entire demand from B, and it's always blowing from one of the two. This means that you have to have enough capacity at both A and B to meet the entire demand. So you're overbuilding in some sense. You've got to build more capacity than you would have if there were no fluctuations. So there's a cost to overbuilding. There's also a cost, of course, to building storage capacity. And another technique that utilities are using for dealing with the intermittency is what's called demand-side management. So a lot of utilities now have contracts with their large customers, under which the customers agree to reduce demand if there's a sudden shortage of supply. So if there's a sudden drop in the wind speed, here in New York, for example, Con Ed, the local utility, has agreements with many of its large customers that they will disconnect some of their power using equipment at short notice if there's a big drop in the supply of power. And of course, they get paid for that. They get paid in terms of reduction in what they're paying for electricity. And in many cases, for example, in many of the large buildings in Midtown Manhattan, you can switch off the air conditioning for a couple of hours and nobody notices. This is a legitimate way of coping with fluctuations in demand as well. And most utilities reckon they can cope with demand fluctuations of plus or minus 10% by this type of method. So let me talk about some numbers. In the scenario that I'm working on, the US would consume 7 times 10 to the 6 megawatt hours of renewable energy each year. And a reasonable amount of storage is 2 days total consumption of renewable energy. That's a complicated calculation to go through, and I'm not going to talk about it in too much detail. But $75 for a kilowatt hour of capacity, which is the number I'm taking. So I'm assuming the cost of storage falls somewhat from today's figure of $100. At $75 a kilowatt hour, there's enough battery capacity to store 2 days of renewable energy consumption would actually cost just over $1 trillion, $1.084 trillion. So as I said, storage has come down a lot in cost, but the storage on the scale on which we're going to need it is actually very, very expensive, $1 trillion of storage. The important point here in terms of the economics is that the amount of storage you need in an energy system goes up very non-linearly with the fraction that's coming from renewables. If you've got 20, 30, 40% coming from renewables, which is what we have at the moment and what many countries in Europe have at the moment, then you don't really need much energy storage at all. There's enough margins you can make adjustments on with the other power stations to cope with fluctuations in supply. As you get up to 60, 70, 80% renewable energy, then the amount of storage capacity you need goes up very non-linearly. And the storage capacity becomes really quite expensive. 61% renewable energy, which is what we'd be if we replaced all existing fossil fuels, is right on the margins of where there's a very sharp non-linear increase in demand for storage. Now, so we've got some costs. We've got the cost of capacity, we've got the cost of storage, cost of overbuilding, cost of building out the grid. We've also got some savings from switching to renewable energy. I'm calling the savings offsets. One is fuel costs, obviously. Solar and wind power, they have large upfront capital costs, but there's no variable costs. There's very little in the way of labor cost, and there's no fuel costs. So if you install wind or solar, it's rather like prepaying for your electric power for 20 to 30 years, and you save on these fuel costs. Now, I've done some calculations on how much we would save in terms of coal and gas if we replace fossil fuels linearly over the next 30 years, i.e. by 2050. And the savings in fuel costs are huge. They're $1.12 trillion. So we're going to say if we move linearly between now and 2050 away from fossil fuels towards a future consisting entirely of renewable energy, nuclear energy, hydropower and geothermal, then we will save $1.12 trillion over that period of time in fuel costs. Another saving, at least another offset, which is a slightly more complex and controversial one, is that almost all the coal plants in the US are going to need replacing long before 2050, as will 20% of the gas plants. Why? Because they're old. Most coal plants in the US were built before 1970, which means they're over 50 years old, and they were originally built for lives of roughly 40 years. So they're being sort of licensed to continue operation on a year-by-year basis at the moment. And there's no way these plants will continue to 2050. So even if we don't replace them with renewable energy, even if we don't go green and go clean, we'll have to replace those coal plants and 20% of our gas plants. So that I argue that means that the cost of replacing these plants should not be regarded as a cost of abating greenhouse gas emissions, because they'll have to replace anyway, okay? And that gives us another offset of $1.01 trillion, because the cost of replacing all of these coal plants and gas plants that will need replacing anyway is just over $1 trillion. So this table here summarizes the total costs if we think about phasing out fossil fuels in power generation in the US. The cost of new capacity, solar and wind capacity, is $1.2 trillion. All these numbers are in trillions. The cost of the storage in order to deal with intermittency is just over $1 trillion, $1.08 trillion. The cost of building out the grid at 100 billion is basically peanuts by comparison with these huge numbers here. So that's the $100 billion I put in for building out the grid. And then we've got savings in fuel. Okay, so we've got a negative number here. We're saving $1.12 trillion in fuel costs between now and 2050. And this is the capacity replacement offset, reflecting the fact that much of the coal-fired capacity and the gas-fired capacity would have to be replaced anyway by 2050. So if we add these things up, if we take both of the offsets, the net cost is only 0.179 trillion. If we take only the fuel offset, and I'll argue about the case for doing that in a second, then the net cost is essentially $1.2 trillion. Now the fuel offset, I think, is logically a legitimate offset, but nevertheless, the fact is that these power stations do have to be replaced, so the cash will still have to be spent. It just isn't properly attributable, I think, to avoiding greenhouse gas emissions. So if you want to get the cost of avoiding greenhouse gas emissions, this is the right number, 0.179. If you want to get the actual amount of cash that's going to have to be paid out net, this is the right number. And if you divide either of these numbers by 30 years, which are 29 years actually, which is the number of years from now to 2050, then the lower number turns out to be $6 billion a year, and the higher number turns out to be $40 billion a year. So the cost of moving away from fossil fuels, the cost attributable to avoiding greenhouse gas emissions is as low as $6 billion a year. The actual cash cost of the order of $40 billion a year. And just for sake of comparison, in 2015, the US capital expenditure on power generation was $42 billion. So $40 billion is essentially what we're spending at the moment. The question is to spend it intelligently. And it's just, I want to emphasize that the biggest, one of the biggest costs, and certainly the biggest unknown here, is the amount that we should spend on energy storage. As I remind you, that was $1.1 trillion in the estimate I showed a couple of seconds ago. And that is a very large number. And there's a lot of uncertainty about that number. Other numbers, I think I'm fairly confident of, but that one has a big margin of error about it. I could be assuming too little storage, and I could be assuming too high a price for storage. Storage costs will probably go down, but we just don't know how much. And we don't have enough experience with using systems with high degrees of intermittency to really know exactly how much storage will be needed. Okay, so that's my first point, the various points I want to make in this talk. The first point is that the cost of going carbon-free in power generation is actually quite low. And that is actually not surprising when you think about it, because the cost of wind and solar power is now very low. It's lower than any other source of energy. The complicating factor is the fact that you have to spend money on energy storage to deal with the intermittency. And so the cost of dealing with the intermittency, as you saw from these numbers, is really quite high. And it's difficult to estimate that with precision. Next thing I want to talk about is carbon taxes. There's very widespread agreement amongst economists that a price on carbon is some sort of a prerequisite to solving the climate problem. We could be a tax, it could be a cap and trade, but either way, there's a general agreement we need to price carbon. And there's widespread discussion of a carbon tax in the range of $20 to $50 a ton of CO2. The California cap and trade system, for example, has floors and collars designed to keep the price of carbon in the sort of $20 to $50 a ton range. Now, I'm going to talk about some results that Wolfram Schlenker, my colleague, and I have recently obtained looking at the economics of a carbon tax. Generally, carbon taxes are evaluated in a static context, but this is a dynamic problem, which is going to play out over a couple of decades. And we've looked at this in a dynamic framework, which means we've used a sort of a Hartelling model rather than a Pigou model, which is the standard framework. I mean, the key thing here is that all fossil fuels are exhaustible resources. They're not produced goods. And because they're exhaustible resources, the kind of considerations that apply in the Hartelling framework are very relevant here. The key thing about an exhaustible resource is that it can be used now or it can be used in the future. You can use it now or you can leave it in the ground and use it in the future. And which is the more profitable thing to do depends on the price trajectory. And it's the price trajectory rather than the price level that determines the supply of an exhaustible resource. So we have to consider that a carbon tax may change the pattern of use over time and take that into account. Now, the paper that Wolfram and I have written is quite a long and complicated paper, so I'm not going to go through the math at all. In the very simplest case we consider, just a sort of a pure sort of Hotelling type model where there's just a simple exhaustible resource, a single grade of it, then we actually show that a carbon tax won't in fact reduce the consumption of the exhaustible resource at all, but will merely delay the consumption. So all of the resource will be consumed, but it will be consumed more slowly. And so the emission rate will be lower, but the integral of emissions over time will still be the same as it was before. And more generally, in a slightly more complicated framework, we find that a carbon tax may make high-cost supplies unprofitable and drive them out of the market. So in the first case, the top case up here I just referred to, there was a single grade of oil or single grade of fossil fuel. I refer to it loosely speaking as oil. More generally, we have many different grades of oil. We have low-cost oil, for example, from Saudi Arabia, which costs maybe $5 a barrel to produce. We have high-cost oil from deep ocean drilling or fracking, which may cost $50, $60, $70 a barrel to produce. And what we find is that a tax will force some of the really high-cost supplies out of the market, but will simply delay the production and consumption of some of the lower-cost supplies. We also find that a tax will have a big impact on coal and gas, but very little impact on oil. Let me explain why that is. So this is a table where I'm looking at the impact of a $50 carbon tax, that's $50 a ton of carbon CO2 emitted, on the various fossil fuels, coal, gas, and oil. So this is the units in which we measure fossil fuels. We measure coal in metric tons, we measure gas in millions of BTUs, we measure oil in barrels. This is the amount of CO2 in tons produced when we burn one of these units of the fuel. So if you burn 1 metric ton of coal, you produce 2.86 metric tons of CO2. If you burn 1 million BTU of gas, you produce 0.053 metric tons of CO2. And if you burn a barrel of oil, you produce roughly 1/3 of a ton of CO2. These are the prices of these things. So coal is roughly $50 a ton, gas $2.8 dollars per MMBTU when I last checked, so roughly $3. And oil somewhere between 60 and 70 dollars a barrel. So if you put a $50 tax on coal, then your tax is going to be 50 times 2.86 because you're producing 2.86 tons of CO2 per ton of coal, and the tax will be $143. So the price of a ton of coal would go from $50 to 50 plus 143, which in round numbers is 200. So you would effectively quadruple the price of coal by putting a $50 tax on. If you put a tax of $50 a ton on gas, then the tax is $2.65 per million BTU, which roughly doubles the price of gas, the wholesale price of gas. Okay, well, as I said, the price of gas when I last checked, which was a few days ago, was $2.8 per million BTU. So you're roughly doubling the price of gas with a $50 ton carbon tax. If you look at oil, on the other hand, a $50 ton carbon tax on oil would cost $17.6 per barrel. This stuff is selling for $60 a barrel or $65 a barrel at the moment. So the total effect on the price is actually relatively small relative to the other two here. And furthermore, the profit margin on oil is huge. As I just indicated, there's quite a lot of sources of oil which are being produced for $5 to $10 a barrel, giving a profit margin of at least $50 on each barrel of oil. So it's very easy indeed for many producers to absorb a tax of $17.6 on a barrel of oil. So you can see why there's going to be a very big difference between the impact of a carbon tax on coal and gas and on oil. A carbon tax of $50 a ton would push coal and gas really out of the market, making them completely uncompetitive. It would have very little impact indeed on oil. What it would do, it would lead to some drop in current consumption of oil, but that would be totally compensated for by increases in future consumption. And part of the problem here, of course, is that the demand for oil is very inelastic. Demand for coal and gas is quite elastic because there are alternatives. We were just talking about the alternatives. Those are, of course, renewable energy, amongst other things. For oil, which is used largely in transportation, there is very little alternative. So the elasticity of demand is very, very low. Okay, this is a diagram that Wolfram and I produced. I think I'll just skip this diagram and go to this one first of all. May come back to the other diagram later on. So this is a key diagram from the paper by Schlenker and myself, which summarizes the really important issues here. On the vertical axis, we've got the required, on the horizontal axis first. Horizontal axis, we've got the desired reduction in cumulative oil use in terms of percent. So if you want to reduce cumulative oil use, for example, by 50%, then we're at this point here. And what this line does is show us the required carbon tax in terms of dollars per ton of CO2. So the way you read this diagram is that if you want to reduce cumulative oil use between now and the end of the century, let's say by 50%, then you need a carbon tax of, come up here and cross here, $550 a ton. If you want to reduce cumulative oil use by 25% by the end of the century, you need a carbon tax of $450 a ton. If you want to reduce oil use by only 10%, you need a carbon tax of still $250 a ton. And if you wanted to reduce oil use by 2/3, then you'd be looking at a carbon tax of very close to $600 a ton of CO2, which is way, way in excess of anything that's been discussed in political policy terms, contexts. Skip this. So that means I think we have to think about alternatives to a carbon tax. If I think about a $600 a ton tax on CO2 emissions, the impact of that on the price of gasoline would be to drive the price of gasoline up in the US to around about $9 to $10 a barrel, a gallon. It would increase the price of gasoline by a factor of roughly 3. It would almost double the price of gasoline in the European market. My sense is that that's probably politically unacceptable. There's a lot of evidence that people are very sensitive to big increases in the cost of gasoline. A smaller, much smaller attempt to a smaller increase in the price of gasoline in France led to the Gilets jaunes phenomenon a couple of years ago, which almost unseated Macron at the time. So my guess is very few politicians will be willing to think seriously about a $300, $400, $500, $600 a ton price on carbon emissions. So we've got to think about something else. Now, we could, of course, go for a cap and trade system. That cap and trade system will always work. The cap will always bind. But of course, what would happen just is that the permit price would be very, very high indeed. So that would be effectively putting a tax on carbon through the back door. And it wouldn't avoid the political issue here. So what are the alternatives that we might be faced with? Well, renewables are a success story. You know, renewable penetration in the US has been growing rapidly. And in Europe, it's been growing even more rapidly. So what is it that has made renewables a success story, and can we copy with oil and with transportation what we've done with renewables? Here in the US, renewable portfolio standards have worked very well. And of course, there's also been at the federal level, there's been at the state level. On the federal level, we've seen the production tax credits and the investment tax credits. So what's driven renewables in the US is a combination of renewable portfolio standards and then subsidies, direct subsidies. Renewable portfolio standards are effectively subsidies, but they're not subsidies that come from the taxpayer directly. They're subsidies that come from the ratepayer. In Europe, the main driver has been feed-in tariffs. Been very, very generous feed-in tariffs indeed for renewable energy in Europe. And they seem to work very well, although they've proven to be quite expensive. And some of the ratepayers are getting upset about the cost of power in European countries at the moment. So perhaps we should rely more on clean energy standards and feed-in tariffs and things like that as a way of transferring demand from fossil fuels to renewable energy. The biggest driver of fuel efficiency, specifically in the US, has been the CAFE standard, the corporate average fuel efficiency standards. And in the US, in the European Union, there's something very directly equivalent to that. And like the renewables portfolio standards, one of the effects of these CAFE standards and their equivalents is it hides the cost of greater fuel efficiency. For example, there's been estimates by Resources for the Future in Washington that suggest that the CO2 price implicit in the current CAFE standards is of the order of $200 a ton of CO2. So we are effectively pricing CO2 from vehicle emissions through the CAFE standards, and we're pricing it at a price which would be probably politically very hard to implement, but people don't really see that price when it's happening through greater fuel efficiency. And indeed, there's an attractive element, a politically attractive element to greater fuel efficiency too, which makes this probably a more politically acceptable approach. So one alternative to carbon tax would be to combine a more aggressive CAFE standards with direct subsidies to electric vehicles and to charging infrastructure. There is an issue here, which is that auto companies are conflicted in this context. You know, car companies make electric vehicles and they also make internal combustion engine vehicles. And currently, at least, they're making a great deal more profit from the vehicles with internal combustion engines than they are from the vehicles with electric motors. So that they're inclined, I think, to put more emphasis on the sale of ICE cars than electric vehicles, except obviously for Tesla. So we need also to make it very clear to vehicle manufacturers that there's going to be a date beyond which they will no longer be able to sell internal combustion engines. So they have a strong incentive to build up the profitability of the electric vehicle fleet. My sense also is that in terms of dealing with buildings, we have to tackle the emissions of buildings by a combination of building standards, which are effectively emission limits, which is sort of a cap on emissions, and direct subsidies to deal with the costs of installing more effective, more energy efficient heating systems. And that simply putting a price on CO2, which is what New York City is trying to do at the moment, will prove politically very, very hard sell indeed. That the necessary price will be too high, that we have to find some alternative there. Now, this runs contrary to a lot of mainstream economic thinking, which tends to recommend taxes and is strongly against subsidies. Most economists don't like subsidies. They do like taxes as a way of dealing with problems of this sort. But we do seem to have got ourselves into a second best situation where the first best just isn't acceptable politically. And so we're forced to look at policies that a standard textbook wouldn't really recommend. Okay, let me end up with some remarks about electricity pricing. As I said earlier on, decarbonizing transport, decarbonizing heating means a switch from fossil fuels towards using clean electricity. And at current electricity prices, this would mean a huge increase in costs. You know, typical retail power price in the US and in the European Union, somewhere of the order of 15 cents a kilowatt hour. And it's rather higher here in New York. I'm paying 20 cents a kilowatt hour here in New York. And California, the price is similar to that, 20 to 25 cents a kilowatt hour. And let me just remind you that I showed you earlier on that the cost of power from solar and wind is $37 a megawatt hour, $40 a megawatt hour. That turns into, that's 3 cents, 3.7 cents, 4 cents a kilowatt hour. So the cost of renewable energy is a very, very small fraction of the current retail price of electricity. It's 3 to 4 cents as opposed to 20 cents. And even with non-renewable energy, the spot price of power here in New York is around about 4 to 5 cents a kilowatt hour, which is way below the actual retail price. So we need, in order to persuade people to adopt electricity on a much more widespread basis, we need a price which reflects its social marginal cost. And when we have a grid which is dominated largely by renewable energy, that social marginal cost will be close to zero. So we're going to need a much, much lower price for electricity in order to get widespread adoption and to complete our decarbonization task. So renewable energy is one of these problem cases where you've got really low marginal costs, but really quite high fixed costs. I mean, all of the costs of renewable energy are fixed essentially. So those fixed costs have to be covered somehow. And the cost of the grid has to be covered somehow too. Currently, those are all bundled into the marginal price. So when I pay 20 cents a kilowatt hour, I'm paying essentially 5 cents for my electricity. The other 15 cents are going towards the cost of the grid and various other fixed costs. But they're all bundled into the marginal price. We need a price much closer to marginal cost in order to get people to use electricity as they're going to have to in a renewable energy world. But then there's the question of, if we price at marginal cost, how will our fixed costs going to be covered? And this is obviously a 21st century equivalent of the problem of Dupuis Bridge. Two-part tariffs are one possible answer, where you've got a fixed charge for being connected to a system which covers the cost of the grid. and is independent of how much you use, and then a variable cost which reflects your actual usage, which could be very low in terms of a smallish number of cents per kilowatt hour. There are probably other ways of dealing with this. We could use direct taxation, for example, to cover some of the fixed costs and treat them as infrastructure, treat the grid as infrastructure, something we have to pay for out of general taxation revenue, rather like we treat roads and airports and so on as part of the infrastructure. Anyway, one way or another, we're going to have to think very hard about how to price electricity and how to cover the costs of providing electricity and managing the grid. We're going to have a lower marginal price for electricity than we do at the moment. We're going to have to think hard about the whole utility business model and how utilities cover their fixed costs. So this is my last slide now. Let me just try to summarize the rather disparate set of points that I've made. First of all, replacing fossil fuels in power generation is really quite affordable. Secondly, decarbonizing is challenging, and the obvious instrument, the carbon tax, is probably politically unacceptable, because if we get it high enough to be really effective, we would have a huge impact on the cost of gasoline, the cost of heating oil, and so on. So we probably have to supplement a modest carbon tax by emission standards for buildings and for transport. Decarbonization means electrification, and with present tariffs, this would be far too costly. So we need to rethink how we price electricity. We need to rethink the entire utility business model. In particular, we need to try to stop recovering our fixed costs from the marginal prices. Okay, well, thank you very much for listening. That's my 45 minutes done. Jim, over back to you.
Thank you so much, Geoffrey.